Hi, it's time to learn about mass movements, mass wasting, and orogenic events. Wow, that's a word, right? Orogenic. Well, we'll learn more about that in a minute. When you see a sign like this one, that should be a warning that you're in an area that is potentially unsafe. They're not just there because people felt like spending money, meaning the government, to put signs there. Those signs are there because there's an imminent risk, or there's already been a problem at this site. So I'm looking at a sign right near Olympic National Park. And as I look at this sign, it says rock slide and avalanche areas next 12 miles. So I'd ask you, if you see a sign like this, do you change anything about your driving habits? Do you slow down? Do you roll the windows down? Do you keep the radio on or tunes on as loud as you can? I might encourage you to rethink that, because at least having your eyes out on that road, at least maybe having the windows down if it's safe to hear, if you hear any cracking noises, rolling noises, feel any vibrations. These are things that matter. But before we can even talk about mass movements and mass wasting, we kind of need to talk about mountain building. And mountain building is what orogenic events is all about. So let's start there. So the first place we start in this conversation is distinguishing how hills are uniquely different from mountains. So this may seem obvious, but it's not, because there are many hilly places that to someone that grew up in Houston, Texas, like myself, might seem like a very large mountain, but they don't qualify. So let's take a look at both pictures here. And on the left, you see a photo of the Texas Hill Country. On the right, you see an endearing place I've been to in New Zealand called Mount Cook. So besides the incredible sunset we took, this was right off of our hotel veranda. So what do you notice about Mount Cook that looks dramatically different than the hills? Hopefully its relief, meaning its total elevation, is higher. Don't confuse that with total relief. Total relief is anything like seamounts that are below sea level all the way to their summit above water. This is total elevation, which is anything above sea level. So that's what we're talking about when we're referring to how tall something is it's basically its total elevation above sea level. In terms of a mountain, that must be a minimum of 900 feet. But there's a second requirement. That is that it has a summit that's distinguishable. In other words, it has a pointed top, right? And hills don't have that. So hills could potentially be more than 900 feet tall. It's just that they don't have that distinguishable summit. You can even see mesas and plateaus and even buttes that could potentially be bigger than that. These are landscape features you'll learn about later in this semester. The point being is you've got to have those two requirements in order to qualify as a mountain. Mountains and hills don't just magically appear. Sometimes they can form because of differential weathering in terms of hills. And the hill country is a case in point in Texas, because the hill country has some cap rock-like geology at the tops of their hills that are a very thick limestone that's dense. Underneath them, they have softer limestones and even shales that are very highly fossiliferous from the Cretaceous period. So they've weathered out into these remarkable hill formations that we recognize as the hill country. But a mountain like Mount Cook forms completely different. And there are different types of mountains. There are subduction zone mountains, there are folded mountains, there are thrust mountains. There's a variety of different types of mountains out there. But we're going to look at a few and talk about how a mountain even can conceptualize being formed. So the first term we have to learn about is what a mobile belt is. Yeah, you heard me right. That's a random term, right? Mobile belt. But let's kind of break that apart. Let's start with where mountains are typically found. They're usually where plates collide. That could be like a continent to continent relationship, or maybe like India smashing into Eurasia, uplifting the Himalayas, which is where Mount Everest exists. Or maybe it could be where you have an ocean plate subducting beneath a continental plate, which is a subduction zone. The point being is they're along margins of continents. So when we're talking about a margin of a continent, we're referring to its edges. And there's a couple of things you've learned thus far that in the semester is that a passive margin, meaning it's not active, passive margins don't have plates that are currently smashing together. There could have been some in the past, and I'll use an example from this illustration. We've had multiple active plate tectonic margins along the North American craton, and craton is a simple term for the major interior section of a continent. It's happened up and down the eastern seaboard, the margin, eastern margin of the North American craton, 4, 5, 6 times over a period of hundreds of millions of years, and before that, billions of years. And then you look on the western margin over here, and we've had the same kind of thing happen, but in a lot more recent geologic time. We still have another very active mobile belt situation that started happening down here in the south called the Ashevtal mobile belt, which started forming when we had Pangea take place back in the Paleozoic. So we need to name all 3 mobile belts. The point being is, let's start with one that is very recognizable to most people, and that's the one over here. So while these are in blue right now, this is a paleogeographic map of North America craton, and it's simply showing where sea level is relative at that time. Obviously, sea level's lower in this picture today than it would have been when this particular time frame existed. So it helps, though, visually see where the mobile belts exist, so you can kind of say, okay, yeah, I get that. I see how it works. So the 3 major mobile belts in North America are the Appalachian. Many people refer to it the Appalachians. In the United States, that's more of an English term, Appalachian, Appalachia, but that's all the stuff on the eastern seaboard. Then you have the one on the western margin, which is the Cordilleran. That includes like the Rockies, even the ancestral Rockies formed in that area, the Cascades, things of the more interior Rocky Mountains that we think of, like the Grand Tetons, all of Alaska, down in parts of Mexico. Then we have another one right in here, which is called the Ashevtal. That extends in to places like Arkansas. And all 3 of them are uniquely different, but they represent a period of places, a margin of the continent, for better lack of words, that it's been smashed into at some point, maybe repetitively. So let's say I have a plate smash in Alaska. A couple of 10 million years later, one smashes down here in Southern California. Well, I'd have a new mountain range there. Then I have another one smash into Washington State and Oregon and Northern California, like Juan-de Fuca's doing today. That would be another mountain. So they're all mobile, meaning the location of where the smashing is mobile. It can change over geologic time. So that's what a mobile belt represents, but essentially they're mountain ranges, and they're for large geographic areas. So that brings us to the fun word called orogenies. Orogenies are specific mountain building events. So they have proper names, just like, for example, the United States or Europe or Antarctica. We have major proper names for specific episodes of mountain buildings known as orogenies over geologic time. So there's been a series of orogenic events that built the Appalachia or Appalachians in this area. And then, of course, we've had multiple series of smashings over here that uplifted variety of mountain building events. Probably the most notable is what created the basin and range and what we know as the modern day Rocky Mountain Range. And that came from an orogeny called the laramide orogeny, and it was an ocean plate that had parts of Juan de Fuca and down here Cocos Plate, which are now, they broke it off of the Farallon, and the Farallon subducted under North America and uplifted at a very low angle, not steep subduction, but a very low angle, about 10 degrees, and it wrinkled and deformed crust all the way inland to parts of Colorado, New Mexico, Arizona, Utah, Wyoming, Montana, Nevada, so Idaho, all of those places. So orogenies are mountain building events. That's all they are. But they are proper names, just like we would name a country. These things have names, just like you have a first name, so do they. And each one is unique to its specific geologic point in time in which we had mountains get uplifted in a specific area of a mobile belt like the Cordilleran, the Appalachian, or the Ouachita. And every continent has multiple mobile belts, and subsequently they all have multiple orogenic events or orogenies. But one thing that's important to point out is when plates do smash, we're going to have what's called crustal thickening. And that happens because you get crust that's thrusted upwards when things smash, just like cars. That causes the lithosphere, which includes the ocean and continental crust and the upper part of the mantle, to be kind of put out of equilibrium, and it pushes all of that up, causing what we refer to as roots or the interiors of mountains, and you can see that in this diagram over here. That means your thickest crust on the planet should be where your largest mountains are. So going back to plate tectonics, that would be where you have two continents smashing together, like the Himalayas uplifting Mount Everest type situations. So for a minute, can you imagine that scenario actually happened in the North American craton when Pangea was forming back in the late Paleozoic? And the answer is it surely did. And we still have evidence and remnants of some of those mountains left behind. The point is the mountain's a lot bigger than what we see at the surface. So total elevation is going to be everything from sea level up to its summit for a mountain, but there's much more that's underground. And I would take a moment to compare this to the Grand Canyon. The Grand Canyon represents a place in geologic past where we had giant mountains during the first formation of a supercontinent called Rodinia. And it thrusted up giant mountains there, and the bottom of the Grand Canyon, which we call the gorge, has a big giant root of a mountain that probably extends miles beneath the surface, but we can see some of that at the river area. It's very distinctive. It's metamorphic and igneous rock. Over time, as mountains began to weather down, weathering's the breaking down, erosion's the moving of that away, the weight of the mountain diminishes because its mass is smaller. That means it's not pushing as deep into the mantle, so it's finding more stable equilibrium, and then it can appear to actually kind of pop back into place. And I'll use the example here in a minute of isostatic rebound from my childhood to kind of give you this perspective. Ultimately, the fate of every mountain is to erode down to sea level. Then maybe if it's along a continental margin, it will thrust back up again when we get a plate collision, which is exactly why we call mobile belts, because the location of mountains changes simply based on where the collision of plates occurs along that big giant stretch of the margin or edge of a continent. So let's talk about continental and oceanic plate relationships. So when you have an ocean plate smash into a continental plate, the ocean plate may be thinner, but it's also denser. And so having more iron and those types of heavier metals in their crust makes them sink when they come in contact with the continent. So sometimes you'll hear the phrase continents floats on top of ocean plates. I don't know if I 100% agree with that. It's more like all of the crust floats on top of the mantle, But oceanic plates definitely will take a nosedive. As that subduction zone occurs and the ocean plate's sinking, it could tear off some of that continental material and carry it down into the mantle where partial melting can occur, which can turn on volcanoes just like Mount St. Helens. You'll be learning a lot more about this volcano a little later in the semester. Likewise, sometimes as an ocean plate subducts under a continent, it can rip off part of the ocean plate and it gets stuck onto a continent. And we can call those terrains, which we'll get to in just a minute. But an ocean to continental plate collision is a subduction zone. And when this occurs, that partial melting and blending of continental crust, which is typically very felsic, meaning it's made of granite and things like rhyolite, it mixes with mafic or ultramafic types of rocks. So in the mafic category, gabbros and basalts. And as they blend, they form a mixture of the two. If we recall back to igneous rocks learning about margarita mixes, this matters here because typically the margarita mixes are fairly high in silica. So that means that they're going to have a more explosive eruption because you've melted really thick continental crust and blended it with thinner and denser mafic material, which is certainly what happened in the case of Mount St. Helens and the other volcanoes in that area, i.e. would be something like Mount Rainier, Mount Hood, Mount Adams, Mount Shasta, and the list just goes on. Throughout geologic time, we have had a number of situations where two very thick continental plates came together, they smashed, and they pushed upwards. This is where you're going to get your absolute tallest elevation mountains, thickest crust on the planet. And the case in point would be something like the Himalayas, which is exactly what you're seeing right here. And the way that forms is, well, one crust of continental may be slightly different in its thickness and also its density. They essentially are made of the same types of material, granite-based felsic stuff. And when they smash, you don't get very much partial melting because they're not subducting back into the mantle. So instead, you get uplift and a big amount of it, which creates a seriously tall mountain range. So wherever we had continent-to-continent collisions in geologic past, such as during Pangea, you should have seen very, very tall elevation mountains that existed there. How do we know that? We have evidence of that in North America during the Pangea formation of when South America and Africa smashed into those, as well as Eurasia smashing into the North American plate. So we were bombarded from basically multiple sides and had very tall mountains at that time. That brings me to the principle of isostasy. If you can say that with me, isostasy, say it 3 or 4 times in a row. What does that funny word mean? Let me tell you my story, then we'll compare it to the diagram we have here. My first experience with the principle of isostasy dates back to my first filling at the dentist. And I liked to go to the dentist to get my teeth cleaned because Dr. Blum was super nice. And he had a little bitty waiting room. So there was a long couch and basically an oversized chair type situation, 2 tables and a magazine rack, and a handful of toys in the corner. So painting that picture is important because my mom and I were kind of stretched out on the couch and we had been there already for at least a good 40 minutes, maybe 45, when this giant human being walked in. And when I mean giant, to me, they looked like King Kong. They were huge. And the individual got my seat on the couch. There was already somebody in the oversized other seating arrangement. Since Mom and I were sharing the couch, I got sent to the floor since I was able-bodied and young. So a little miffed anyway, I get down there and I'm playing with the toys and 45 minutes goes by and then the individual gets called back and I'm like, well, we're waiting forever. My mom's getting a little restless. Turns out the individual was getting a root canal. Knowing what I do today, I think I'd volunteer to wait another hour for my procedure over theirs. But here's the fun part of the story. When the individual got up, so mind you, my mom's all the way on the other side of the couch. The person stands up and it leaves a big indentation in the cushion. So this was back in the early 70s. And so the couches, it was like a vinyl couch back then. And so this person stands up and I'm like, Mom, look at the couch. It's been ruined. There's this just like giant hole in it. So I got the old stink eye, right, from the individual thinking, how dare you? Are you calling me some kind of name? I mean, it had nothing to do with the person. I was just really concerned about the couch. About 30 minutes later, the couch pops back into place. And I'm like, Mom, look, the couch is rescued. It's gotten back into its original shape. And my mom started laughing. And she went, yep, that's called the principle of isostasy. And I'm like, the principle of what? My mom was a scientist. My dad was a scientist. So while they were in the biology field, she certainly knew what the principle of isostasy was. And she explained to me, when you get something that's heavy and it's weighing down on something, i.e. a mountain onto the crust of the earth, the mantle, here's a good diagram of that, it's going to smash it down. When that is removed, that allows new equilibrium to be found and it pops back into place. That is called isostatic rebound. Rebound happens after the weight is gone. So a mountain range like the Appalachia, what I grew up learning as Appalachians, but it's Appalachia, the English pronunciation, it's actually rebounding a bit from isostatic rebound. It doesn't mean that it's still having an active plate collision like the Himalayas. Those are actually uplifting by centimeters a year because the Indian plate is still smashing into the Eurasian plate, causing those mountains to rise in spite of gravity, weathering, and erosion. But as your mountains erode, or let's use another example, you have continental ice sheets, and they're going to press down on the crust and do exactly the same thing. And when they melt, the crust can rebound back into shape. That's called isostatic rebound. That's a big part of understanding how mountains work. Another important concept for understanding how continents grow is something called accreted terrains. Let's kind of get this word right. Accrete. Accrete is a term that means basically join or glue. So when you get a landmass that's out in the ocean and it is being pushed by a mid-oceanic ridge into a continent and it smashes onto it, some of it's going to tear off and go down via subduction, and anything that was like ocean sediments or whatnot gets smushed up and accreted or glued onto the continent. It also could be that you have a seamount out here, like an island, and it gets stuck on and doesn't completely subduct. When we look at each of these accreted terrains, you'll notice that we get one color here, one color here, one color here, one color here, and then the continental craton. I'm not saying that the terrains are different colors, but sometimes they are. The rocks may be different colors, like some are called green belts in the North American craton, and they represent some very special rocks that are like serpentinite and rocks that are high in olivine and other types of ultramafic minerals. What I will tell you is that each one of these is separated by a fault because as those flat rock layers that were underwater get shoved and uplifted, they're going to create new landmass that attaches onto a continent. And like I said, you could also have that ocean seamount or landmass. Let's just say a giant Madagascar is over on this side of the continent and it gets pushed into a continent and it could glue on. That is called an accreted terrain. So accreted terrains can look like this. This is actually the Northern Cascades National Park area, and these mountains are the result of accreted terrains. So I can remember I took a cruise with my parents. I actually took them on a cruise to Alaska on the Inner Passage. But one of the things on my dad's bucket list was to take a train ride from Anchorage all the way up to Denali National Park, which is in the middle of Alaska, because he loved trains. And so we did that. So even though my dad had macular degeneration, which basically meant he could not see very well, he had most of his eyeball was blinded out and he could see a little bit around the rims. What he could see was that the landscape dramatically changed as we were taking our train ride from Anchorage at the coast to the interior part of Alaska. And Alaska is like one terrain sandwiched up against another. It's a series of them. And I was like, Daddy, what you're seeing is what we call exotic terrains. I know that sounds funny, but exotic terrains they have different fossils, different rock types, they are different ages. They get literally stuck on to a continent during some kind of plate collision. And it made sense to him. He's like, okay, yeah, I get that. And so along the edges of most of North America, we've had a series of accreted terrains that have added on mass to the original craton, or the interior of the continent. You might be thinking, well, how come we don't have just one big giant continent that covers everything on the planet? You have to go back to plate tectonics. Remember rifting, like rift zones on continents and then mid-oceanic ridges? Those help push plates into subduction zones. So that is why we constantly are recycling ocean material, but it's the continents that are super old. So this is just a generic map from the National Park Service about accreted terrains. And I tell you, we have a lot more than that's showing this, but we're really focusing on the western or Cordilleran range. This is Alaska, which would be way up here. Just on this map, it shows down here. And all the colors correspond to add-ons, stick-ons, and they are sections that happened when we had plate collisions in geologic past. So we will likely have future terrains that get made that look different from the rocks that exist today. And future geologists will be able to decipher those by looking for fault structures, rock deformation such as folding and faulting that you just learned about in the last chapter section. So that's what we look for, because it helps piece together a historical clue and timeline for what went on in geologic past. The terrains and origins of mountains matter. So this is Alaska again, and you can see the various colors. I put even a legend down here below, and I don't expect that you'll know them. The point is that there are multiple terrains that exist in the state of Alaska. Terrains must, by definition, differ from the interior of the continent in their fossil assemblages, meaning what fossils exist there, and their structural trends, and even magnetic properties like magnetic striping, if they were formed from magma that had iron that could align themselves with magnetic north. But essentially, terrains help us as scientists piece together the mysteries of what happened in geologic past. That brings me into looking at a handful of North American mountains. We could spend an entire semester doing nothing but looking at the geomorphology and mountains that existed in North America, but we're going to keep it short. These are some endearing mountains to me because I love Grand Teton National Park, which is in Wyoming, and that's what you're seeing here. More to come on that when we get to glaciers later in this semester. But they're part of the Cordilleran Range. So as we go through these mountains, a few things I might point out. You're going to need to know which mobile belt are they in. Do they have a qualifier, like they're the youngest or the oldest? Are they experiencing isostatic rebound, or have they completely eroded down and maybe been re-uplifted again? That's what we're looking for. And we'll start with one of those examples, the ancestral Rockies. So the ancestral Rockies on this paleogeographic map represent the time frame as Pangea was coming together. So let's kind of piece together what we learned already. Can you see big, giant elevation mountains here? Because we've got parts of South America and Africa and Europe smashing into North America, uplifting just giant mountains. So this side over here, these would be examples of potential areas that could accrete onto a continent. This was a mountain range that was formed called the Ancestral Rockies. That no longer exists today in terms of there being any mountains with over 900 feet in elevation and a distinguishable summit. Instead, they've weathered and eroded down to sea level. But today we have mountains that are known as the modern day Rockies that are in a very similar place. How do we know the Ancestral Rockies existed? First, we can find the faults. We can find the terrain markers. We can also find the weathered and eroded rocks that make the formations that exist all the way through the Southwest. So without the Ancestral Rockies that formed during Pangea timeframe, we wouldn't have the beautiful rocks that people go to see in places like Zion National Park. That brings me to the modern day Rocky Mountains. So the laramide orogeny that I mentioned earlier came in at a very low angle of subduction, and it lasted for tens of millions of years. At the tail end of the Cretaceous period, so the Cretaceous period ended around 66 million years ago, so it started literally at the end of the Cretaceous, end of dinosaur time frame. Then it moved into the section of what we call the Paleogene of the Cenozoic, and it came in at a very low angle. We're talking about 10 degrees or less. Most subduction zones are substantially steeper than that. In doing so, this plate comes in at a fairly low angle, and you can see in the diagram a flat subduction is what it's called, and it uplifted the Colorado Plateau, which had thousands and thousands and thousands of feet of sediments that existed for hundreds of millions of years, including the worn down ancestral Rocky Mountain rock layers. But beneath all of that, literally miles beneath it, were things like the gorge of the Grand Canyon. So the pushing up of the Colorado Plateau kind of fractured and faulted all of those rocks and then started allowing for the weathering and erosion. Now, the modern day Rocky Mountains are block faulted mountains, so they actually make what we call Horsten grabens, and you learned about that in our last lesson. But the key about this particular mountain range is it's in a place that's not typical. Most mountains are along the margins of an active plate boundary, like on the Cordilleran side. If this mountain range would have been at a steep angle, the subducting plate, the mountain range would have been along the coast or close by it, not 600 miles inland. So that's why the modern day Rocky Mountains is significant. Mount Rainier is another famous mountain. So it's just a mountain that's part of the Cascadia subduction zone. And there is a beautiful national park. This is it. I'm actually in the riverbed there taking a picture of Mount Rainier. I'd go back in a heartbeat. It's on my top 5 places of national parks that anyone should visit. But it's a subduction zone volcano just like Mount St. Helens. In fact, it has many histories of eruptions, not just volcanically, but lahars, indicating that this thing has been very busy over geologic time, as long as that Juan de Fuca plate has been subducting under North America. And it continues to do that, so this is certainly an active system. How do we know that? The lava flows are very recent, some of them towards the top. We have recent lahars that are as recent as 1,000 years ago. And so this thing certainly is one that we should keep an eye on. All right, the Ouachita Mountains. Remember learning about the Ouachita Mobile Belt? This one's along parts of Oklahoma and then throughout western Arkansas. It's dear to my heart because I used to go to summer camp at the Ozark Mountains, and that's located in the Ouachita Mountain Range. What happened was you got really significant rock deformation that occurred in Paleozoic aged rocks when Pangea formed. So this is important because South America and Africa smashed kind of from the south and from the east and pushed up mountains and places that didn't always have it. Usually along the Appalachian side, we would get mountains that formed up and down that mobile belt. But since we had some come from the south, we got a new mountain range or a new mobile belt called the Ouachita. Then let's talk about some of the oldest mountains in North America, which are the Great Smoky Mountains. And why are they the oldest? Numerous plate collisions have happened along that Appalachian mobile belt that's on the east coast or eastern margin of North America. But during the Paleozoic, matter of fact, starting in the second geologic period of the Paleozoic, the Ordovician, we had mountain building in the Ordovician and the Devonian and the Mississippian and the Pennsylvanian and the Permian. And so we had lots of mountain building that occurred throughout the eastern side of North America. But at the close of the Paleozoic, when Pangea was fully assembled, the Great Smoky Mountains were uplifted. So they've had lots of time to weather and erode down, and that's why they don't look like the Rockies or Mount Rainier that had very pointed mountains. Instead, they are more hill-like, but they're still mountains. They still have summits, but they are much older. And remember me saying that they're kind of popping back into place because they've weathered and eroded down so far that they're experiencing something called isostatic rebound. Linking back to my story about the couch at the dentist office. That brings me into mass wasting. So we've learned about mountains, we've learned about how they form, we've learned about orogenic events, we've learned about mobile belts. So mass wasting is not restricted to mountainous regions, but it's super common in them, and you can imagine why. The first thing I would say is if you see blinking signs like this one, so we were coming into Grand Teton National Park the last time we were there, and this sign was on in multiple places that we went. And there was reasons for it because there had been some rock slides, some landslides that have happened. Sometimes mass wasting is very imperceptible to the eye, very slow, and other times it's very rapid. So we're going to look at types of mass wasting, and this follows along in your chapter so you can kind of read about the various types. But I want you to heed the warnings that you see in signage. Sometimes I feel like we don't take that seriously. Like I can tell you how many times have I driven by a yield sign and just kind of went, okay, big deal. I don't do that with these signs. I take them seriously because I have actually seen what happens to people, cars, houses during mass wasting events. Sometimes it can be life-changing, if not life-ending. So not to sound dramatic in that way, but that's why we care. Part of science is to try to help mitigate circumstances that could be very hazardous to humans. And certainly mass wasting is one of those circumstances that we can do a better job by implementing some best management practices known as BMPs, as well as signage, as well as education, and as well as maintaining those best management practices. So what is mass wasting? Basically, it's the downslope movement of any kind of material under the influence of gravity. Look at this section at Crater Lake National Park in Oregon. I mean, you can see it, right? I mean, there shouldn't be any like, okay, yeah, that's problematic. I'd be concerned those big boulders might roll into the road. And of course they do. What you couldn't see in this picture was just down from here, it is packed out snow. So this hillside not only is barren of vegetation, it's very full of water from melting snow, which means there's a higher risk for not just rock sliding or in rock landslide movement, but also for heaviness to the sediment because it contains more water. There are a group of factors that influence mass wasting. But essentially, mass wasting cannot happen unless you exceed the angle of repose. What do I mean by that? I would use an example of bench pressing weight. So you're at the gym, you're lifting weights, you're bench pressing. And if you've ever seen anybody lift just a little more than they can actually push up and they don't have a spotter, you know what happens. They exceeded the angle of repose. But in mass wasting, that means downhill, right? So there are different degrees of angle of repose, and what I really mean degree in terms of dip, right? You just learned about dip in our last lesson, how steep something is. Different materials, like even types of sand, have different angles of repose. So it's important to realize that mass wasting can happen anywhere. Gravity is always an influencing factor on the Earth, but certain things can lead to faster, also more egregious types of mass wasting that can wreak havoc on human lives and structures. So let us investigate that. This is a United States Geological Survey risk factor map of landslides. And this is just landslides. So we're not talking about all the other types of mass wasting that you'll be seeing in just a few moments. But you can even see that there's a correlation between mobile belts for sure, right? Like the Appalachian and then the Cordilleran and mountainous areas, but even in Texas, even places along coast in Florida and in the Northeast have that. So mass wasting's everywhere. You just have to know what to look for. So we're going to look at the factors first that affect the potential for mass wasting to increase. So basically, these are things that if they're all in place, or even one or two of them, the likelihood of mass wasting percentage goes up. Slope is probably the number one factor. The steeper the slope, the more potential you have for mass wasting to occur. And that's like, yep, I get that. That's a pretty straightforward thing. But slopes are affected by a number of factors themselves. What kind of sediments are they made of? Are they well compacted? Are they loose, like big talus slopes? Are they embedded with a lot of snow, so the snow melt can actually add weight to them? Are there human structures built on the slopes that could cause overburden that actually can cause the thing to slide or to lose footing? These are all things that matters with slopes. So obviously, the steeper the slope, the more likely you're going to have mass wasting. Not saying you can't have it in flat areas, because we do. Climate is also a factor for what happens in mass wasting. So when you take a look at this type of landslide right here, whenever we have snow melt in the spring, areas that would normally probably be as prone to mass wasting, except on maybe rock slides or potential rock falls, we can actually get catastrophic landslides because big sections of the land can just become saturated with water and start moving downhill. Humid climates tend to yield this, but they're not exclusive to humid climates. You can get big mass wasting and landslide events out in the desert, so you need to know that as well. Water content is a huge factor in causing more mass wasting and faster mass wasting, and I might add more devastating mass wasting. Soils that tend to have more pore spaces between the rock spaces, meaning when we get into groundwater, we'll learn about porosity and permeability. So pore spaces hold water like a sponge. The more a soil can do that, so typically clay-based soil has a high percentage of porosity, it can hold water very well. So as like snow melts, well, we don't have a bunch of snow except on certain years in Texas, right? Maybe if you moved even to Oklahoma or certainly into Kansas and Nebraska, start going up the plains, anywhere in the mountains, you can get snow. But this is an example of permafrost right here, where soil has been frozen, and as it's thawing, this is going to cause a potential mass wasting problem, because remember, steeper slopes tend to have more mass wasting. The water content adds weight, and that weight is also going to cause things to move downhill. You put all these factors together, they spell trouble. This one's a no-brainer, right? The more vegetation you have, the better anchored sediments are in place. This has like none. So this is an Olympic National Park. It's on the rain shadow side of the Olympic National Park. So on one side, it's like literally a temperate rainforest, and on the other side, it looks like this, big giant mountains. But you see evidence of mass wasting right there. I mean, you can see that recently there's likely been some kind of snow melt, and I will tell you this picture was taken maybe 3 days after I took the one at Crater Lake. And so you can see that Obviously, there's been some kind of like snow melt situation. The land was very wet. The ground was wet. There was no vegetative cover. This is a mass wasting recipe in the mix. All we need is something to exceed the angle of repose, and you're going to get mass wasting. Overloading is another one. So the picture on the left is from New Zealand on the South Island in Christchurch. Now, the houses themselves may not have actually caused overloading or too much weight from human-made structures, but certainly when they had an earthquake, it was too much weight, and the triggering mechanism caused these homes to collapse onto the coast. The other picture was of some people who came out to this overhang, and this is in Glacier National Park. And this is a good reason why you should never walk straight out onto an overhang, whether it be rock or it be along a river or something like that, because you don't know how much has been eaten away underneath what you're standing on. These people, while I was doing a lecture in the river, and I had a group of people watching on the bank safely, and I was just saying as these people were walking up, don't do this. Don't get out there, and certainly get on your stomach if you do in case it were to collapse. And there's a pretty good clue in the back that overloading has already happened along this river, and you can see it right here. This tree did exactly what this one used to stand straight up, but it fell over. So if you were one of the people in this picture, you should remember this. If you're not, don't be these people, because they easily could have gotten into some trouble with mass wasting. And I just want you not to be in a situation where you could get hurt. You're like, well, they wouldn't have fallen that far. That's true, but what if the tree would have fallen with them? Then it could have really caused damage. All right, we're at Glacier National Park, and we're just at one of the road stops here on a little hike, and this is what we found. But I wanted to focus on this thing right here for a second. This is why you never walk out onto the edge of a bank that you can't see underneath of. You look at that and you're being like, okay, that'd be kind of dumb, but you're fixing to watch somebody do this very thing. They're walking right out there like their weight could really be held up. We got like 4 individuals walking on it now. And that could be a problem. Eventually the angle of repose will be exceeded and this thing will collapse, just like this tree has back here. In addition, I want to point out this is a braided stream, and braided streams are characteristic of glacial melt. As I kind of scan through the area, you'll be able to see that there are multiple streams in place, and they're braided, meaning there's not just one stream or one tributary. And you see a lot of point bars. That's very characteristic of glaciated streams. We'll see you at the next stop. One more look at what not to do. This is what you don't do when you're at an overhang bank like that. Triggering mechanisms are the last factor, and they are very significant ones. So if you get any of the other criteria that we looked at, factors in place, maybe you have a rocket launching location in your town or city and it vibrates the heck out of the land. Certainly the case near Waco. Or let's say you live in an earthquake-prone area like this place in Christchurch, New Zealand on the South Island. If you get vigorous shaking of the ground, let's say somebody's dynamiting out for a rock crushing operation, any of these factors could produce problems that could cause mass wasting to occur. So triggering mechanisms can often lead to what we call rapid mass movements. And when that happens, rapid mass movements are unpredictable and they happen at a moment's notice. So let's compare the risk of mass wasting here. And let's start on the right. We definitely have mass wasting on the right. You're like, well, it doesn't seem that bad. It would be if your house was just right up from that. Let's say this structure was right here. This stuff could work back towards this house, by the way. But we got better vegetative cover on the right than we do with the stuff on the left. We don't have quite as steep a slope. Probably not as much water in this area as we did right here. The climate's somewhat different. So you're starting to add these factors together. In either case, we didn't have a triggering mechanism. But I guarantee you the mass wasting is going to be faster and more unpredictable on the left picture like you see near Crater Lake, then it will be over here. So that moves us into mass movement risk. This sign should look familiar. You need to pay attention to signage. It's the very first way to combat not being a victim of mass wasting. Mass movements include things like rock falls, rock slides, mud flows, creeps. Yes, and we're not talking people creeps, we're talking geology creeps, and other types of mass wasting, and they can affect landscapes, and I might add human structures and lives. So the imminent threats that pose to humans, that's why these signs exist and why you should care and why you should pay attention. So let's start with the fastest type of mass wasting, which is a rock fall. So I got a question where someone asked me, what's the difference between a rock fall and a rock slide? It's a very good question. And there's several different things. Rock falls are individual rocks that came off of a profile, like a rock profile, maybe a canyon wall or a mountain. They could have been sitting way at the top, or they could have broken off at the side. But typically, a rock fall involves just a handful of rocks, like one or two rocks. It's not an entire mass section of it that releases. In either case, though, this could cause an imminent threat to human health, right? Not to mention the environment. So when you see signs like this that show rock fall hazards or watch for rocks, that's because rock falls, rock slides, landslides have been in the area. This rock right here, by the way, is like this one here, and it came from up there. All right, let's look into rock topples. These happen, and typically they're not going to be as devastating, but they can certainly bury a house or a group of houses if you built right underneath it. But typically they happen along roadway outcrops where humans have blasted out material to build a road. So when the front section of a rock begins to separate and fan out like a deck of cards, that's going to cause more weight to pull and pull and pull, and it separates until the angle of repose, you got it, that large block separates and then falls away from the main bedrock. That's a rock topple, and the diagram shows you how that works right there. So we just looked at rock topples. Now we're going to get into rock slides, then look at landslides and slumps. Rock slides occur along a planar surface, a flat surface, and what happens is you get a failure point of usually bedrock, and this is Zion National Park. And in that flat surface, when it lets go, it literally sends everything off the cliff face or the mountainside. So instead of just being like a rock or the fanned out area of a rock topple, so it doesn't qualify as a rock fall, it doesn't qualify as a rock topple, it's something much more significant, which is a rock slide. So I was here this year when this happened, and it blocked out the park just literally not too long before we had field course that was supposed to go out there. And we were going to have to look at alternative routes, but it was a very wet period of time. The snow melt added to this problem, and then there's lots of chemical and physical weathering. So all of these things factor into having problems with mass wasting. The landslide issue, let's take it a step further than rock slides. You're like, well, they look very similar. They're similar, but they're not the same. Landslides have that one weak zone, and the bedrock literally just moves and takes everything with it. We're talking not just rocks, trees, mud, every kind of earth and soil you can think of, anything in its path, and it just goes squat at the bottom of whatever it happened with, typically burying massive amounts of material at the bottom of whatever elevated region it's in. So let's look at a very large landslide in Washington State, and this happened, and it started way up here. See how that looks different from the rock slide that we examined in Zion? Matter of fact, the sad part about this is people lost their life in this landslide, and every year people lose their lives to landslides, sometimes in some years much more than others. But landslides are problematic, and especially when there's been triggering events like an earthquake that can really add problems for landslides. Then you add in problems with, at the end of spring with snowmelt. All of these factors yield potential devastation when a landslide occurs. Which brings us to the last type, which is called a slump. So unlike a rock slide that had a flat planar surface, this one has a curved surface, and it can do something like you see right here, and you're like, no, that doesn't look so bad. It would be really bad though if your house was built right behind it or there was a major highway, which certainly does happen. Sometimes it can be just as minor as this, but that still is right by a highway and you can imagine could wreak havoc as well. But remember, slumps are along curved surfaces where rock slides are along planar or flat surfaces. So linking back to kind of separating the landslides, the slumps from rock slides, I want to show you a before and after picture of Zion that happened the very same year that I showed you the other landslide just a second ago. This is the before, this is after. Can you see a difference in coloration, especially right in here? Because a big section of that literally flat surfaced slid right off. That is a rock slide. Had it been a landslide, we would have probably seen the entire profile of the side of that mountain just let loose in a moment's notice. So doubtful you would see as much of a landslide in somewhere like Zion as something like a rock slide or a rock fall. We still need to look at some flow movements. Flows are where mass wasting material actually moves. It doesn't just instantaneously happen, it actually travels a distance. So now we got to get into the flows. We've looked at rapid mass movements and slides, and we're fixing to move into the flows. So mud flows are the first, and we know that there's several different kinds of mud flows, but we'll just stick with the name mud flow for now. When we get to volcanoes, a volcanic mud flow is called a lahar, just as an FYI. But mud flows must have 50% sand, silt, and clay, and at least 30% water. So if you get a higher percentage of water, as a more than 30%, it's going to be a more fluidy mud flow. If you get less, closer to the 30, it'll be more viscous or thicker. The point being is mud flows typically follow the path of least resistance, which will be river channels, roadways, stormwater conveyance systems, things of that nature, which is exactly what you're seeing in this picture. And as they approach flatter land, they start to fan out and they can become something called a debris flow. Which brings me to debris flows. When you get thicker and bigger stuff that is just not nearly as able to flow as fast, they can become a debris flow. So mud flows can definitely turn into debris flows as they reach a lower topography area. But unfortunately, debris flows still move and they still can bury homes, buildings, structures, and people in right where they were when this happened. They can travel up to 35 miles an hour. Mud flows can travel much faster than that. So you can imagine if they can pick up everything along the way, they're kind of like a giant bulldozer and they're pushing everything and moving them in a direction. Eventually, they'll kind of solidify unless they keep having added a little bit of water to keep them moving. So debris flows are dangerous, and I would tell you though, you probably stand a fairer chance of surviving if you're not in the immediate path and can evacuate from a debris flow than you would a mud flow. Mud flows can happen in an instant's notice and not be ready for it. One of the most common types of flows that people see regularly, especially in humid climates, are earth flows, where you get the material under like grass or ground cover that starts to migrate underneath it and begins to start what we call, you would say, a slump at the end. That's exactly what's happening here in this earth flow right here. And so in Waco, a very famous earth flow exists in Waco, Texas, along Lakeshore Drive. And repetitively, they've had to shut down Lakeshore to make repairs to the road from where the earth flow has been coming down that steep hillside. It even had to condemn some houses at the top that have beautiful lake view verandas that can look out onto Lake Waco. Point being is that earth flows are very common. There's a special type of earth flow that can happen in only areas that have permafrost. Let me underscore that solid fluxion must involve melting permafrost. So as permafrost begins to melt, it makes what I would call earth flow galore. And it's the stuff that's moving underneath the vegetative cover. You'll see this very commonly. It's in Iceland. It's in anywhere that has permafrost in the Arctic region. So I've seen it in Europe. I've seen it in New Zealand. I've seen it in a number of places. And you get this material moving underneath it. And unfortunately, if people build their structures in the winter and don't know that solid fluxion can parts of it defrost, they could actually see their house move downhill. So this is an important thing for areas that have permafrost. All right, my personal favorite of all the flows are creeps, because a creep is in the neighborhood. So why are creeps such a big deal? They're the slowest type of mass wasting, unlike a rock fall, which is the fastest. Why are they so slow? Basically, as seasonal soil changes happen, the ground can slowly, imperceptibly to our eyes, begin to move. There's some clues that would tell you a creep is in the neighborhood, and this is the best one right here, bent tree trunks. So eventually, this slope will have failure, and when it does, we could have a serious mass wasting event occur. But until then, creeps are just going to continue to do their thing. So you might wonder, why do the trees have bent tree trunks? The trees are always looking for direct sunlight, so they'll actually grow that way to get better sunlight as the creep is moving everything at an angle downhill. So I saw these near Crater Lake National Park. I've seen them all over the world, and FYI, if you're buying a house and there are trees with bent tree trunks in your yard or yards near you, just go to the next one, because these can wreak havoc on a foundation of a home. Some other clues you might see. I used to live down a street near China Spring where Culpeper, if you're ever out that way, the telephone poles are at an angle like this. And those are evidence of creeps. Another thing, you start to see fences that are at an angle, and they can literally fall over as the creep continues to move. Fences, or maybe even rock fences. And I would even say you can see this with cemetery markers and other types of poles that are signage. They all can be affected by creeps, and so can homes. Just FYI. So there are a couple of other movements that we need to talk about. Liquefaction. When you get a rapid movement, and it typically is associated with an earthquake, and you've got clay-based soils and a shallow groundwater source, it can shake that really fast, right? And what will happen is the clay molecules will lose their cohesion to one another. They can no longer stay bound to each other, and that causes everything to go to mush. And this is exactly what happened in Christchurch as I drove along the coastline there from an earthquake that happened. This is the same earthquake in Christchurch, but a shot that I took of a picture hanging in the museum from Quake Museum. And all this water came up to the surface as a consequence of what we call liquefaction or quick clays. They're one and the same type of situation. These can literally make buildings fall down. So liquefaction is a serious issue that's associated with a type of mass wasting that's very sudden and unpredictable. Avalanches are the other type of mass movement that we'll look at, and not all avalanches deal with snow. You need to know that avalanches can also involve other things. You can see avalanches in glaciers. You can see avalanches with actually rock material, but avalanches are most common with snow. But bottom line is they rapidly move, and as they do, they're coming downhill at 10 miles an hour. They break free of their environment up at the top because the angle of, repose got exceeded, and all of that has to go somewhere. This is really dangerous in areas like bowl skiing. So if you like to ski in cirques, which are the bowls or the heads of glaciers where fresh snow is packed out there, avalanches are super common. You need to know the areas in which you're skiing, you're hiking, you're living. Avalanches can also occur as climate warms in an area. So especially in later spring months, you should be on the lookout for avalanches. If there's been overburden, too much weight on the top of a system, that can actually cause an avalanche, some kind of blast or, some kind of activity up there. So here's some evidence of mass wasting. This is at my favorite restaurant in Ruidoso in the parking lot. And you can see the biological weathering there, and you can see how the rocks are failing. What you can't see is the slope is like this. So it's just a matter of time before some mass wasting event happens and wipes out my favorite restaurant in Ruidoso. Just saying that we don't park in this area when we go there. We intentionally avoid it. But if we were to have some kind of rapid mass movement, maybe it would just be localized to here. But when you see these things, they're clues, and you should need to pay attention that they're there. Remember that rock fall from earlier? That's a clue that mass wasting has already happened in the neighborhood. Always look, listen, because you never know when mass wasting can present itself. This talus slope down here is evidence of rocks falling off of this cliff base. If you see rock accumulation like this, mass wasting routinely happens. Another clue. Never think it can't happen when you're there. Every victim of mass wasting didn't think it would happen to them. Here's one of those giant rock slide areas I was talking about of Zion. And can you see the mark right here where this whole section slid off? That's not a landslide. It is on a flat planar surface, so it would be a rock slide. When you drive through the western part of the park, you can see all of the rock material at the bottom of the ravine that came off of this thing. And it's dangerous. Be careful when you're in areas that are prone to mass wasting. Your clues here. There's no vegetative cover. I can see some rills and gullies. You learned about them, and soils and sedimentary rocks. This is very disturbing to me because it's along a major highway. And if I saw this and knowing the slope looks just like this, I would be concerned that this could give way, especially if it snowed and you got a lot of water content in there, because there's no vegetative cover. It's a clay and ash-based rock material, so it holds that water very well. The ramifications of mass wasting are huge. So I'm going to be sharing some video clips of mass wasting that we witnessed during monsoon season out west. And these two shots are of Ruidoso, and I'll show you some video footage as well. But what happened was this creek and river doesn't normally flow like this. And it literally took out a bridge, and a bunch of storm debris built up behind that bridge till the angle of repose was exceeded, and the bridge literally failed, and all of that storm debris and water just went up on the banks and filled in numerous homes. It was devastating to watch. So we're in Ruidoso, New Mexico, and they have just had an unbelievable amount of rain, and it's flash flooded in the area, and we're actually up in the upper part of the canyon. So I'm going to show you a house. And this is what happens when flash flooding occurs. Yeah, not a good thing, huh? So this is all storm debris. And just so you can see that it's not just this location, it's the other sites just like it. All right, so these work crews are dealing with the area, and you can see it wiped out an entire bridge. And this is what we've got left. And it's still going. So these crews have been working around the clock. You can see where the bridge was and where it's not today. And this is mass wasting at its best. So just another look at another shot as you kind of see what this has done and what it continues to do. Look at the color of the river and notice how turbid or brown it looks. That's from all the sediment and stormwater runoff Another mass wasting event happened a week before that. The event happened before we got there, and we weren't even sure we were able to get in the park because it had really impacted the park. But this is on the western side. We saw some similar stuff on the eastern, but not nearly as bad as we saw in the town of Springdale. So basically, the campgrounds that people stay in, the main part of the park entrance that people walk into to take the shuttle buses up to the places you hike, mud flow came through because of a burst of rain from monsoon season and basically buried the town in mud. And it required a massive cleanup. We were there for the cleanup. This is a motel type of RV park and campground. This is the actual pool, swimming pool. This was their check-in area and their store. And you can just imagine what this looked like. And we got to see the cleanup crews doing this. This is some of their kitchen material that they had. And I'm wanting you to get the gist that this was not some small event. It literally filled their first floor with mud. And this was what it looked like through this entire section. So as we drove through the campgrounds that I've taken people to stay at on field course for years, I was floored at how fast and devastating. I'd never seen one like this happen at Zion. But it's just a reminder that mass wasting can happen anywhere, even in the desert. I'm at the Virgin River in Zion National Park 2 days after flooding. And literally everywhere I am into the campgrounds has been flooded out. The water's receded, but I want you to take a note of the color of the water, how turbid it is, meaning it has a lot of sediment. And as I make kind of a turnaround here, I'm just going to show you that all of these banks had been jumped by water. It flooded in the city of Springdale. And I'm just going to kind of gradually work my way up here. You can see Scott up there. He is standing way past where, water went way past where he's standing. So all these boulders and stuff, they came up from the rocks above, and they've also been picked up by the Virgin River during flooding. So this is at the main gate coming into the visitor center, into the section of the park from Springdale, and you can see that there's lots of work being done for the cleanup of the flash flood that happened 2 days ago. This whole area was flooded out from an inch of rain in an hour. So it can happen in the desert in literally a moment's notice. This is Zion again, showing you the amount of debris that had to be cleaned up just to move off the road so people could get in and out of the park. This was a very big event in terms of mass wasting, one that we should never underestimate. This is an area where people park, hike, and also, I might add, campgrounds. It's just scary to think about what happened in such a short period of time at Zion. This is a cleanup at one of the city buildings. There was a library, the city hall. In fact, we saw a media crew there with the city manager and mayor talking about the damage that had been done just a day or two before we arrived at the park. And these are people cleaning up the mud that inundated these buildings and wreaked havoc on the city of Springdale and Zion National Park. Mass wasting is a problem. This created basically a mud flow because of flash flooding and brought all of this mud from the rock formations down into the lower valley where the Virgin River exists. Something that none of us should take lightly. We don't think about these kinds of things being a reality in the desert, but it certainly can be as evidence of what you've seen here. So let's apply what you know. This is a beautiful place, right? This is Jenny Lake, my favorite place in the Grand Teton National Park in Wyoming. While this looks beautiful today, there's a lot of evidence that mass wasting could occur at any moment. Steep slopes, some of them have absolutely no vegetation. There's fractures and faults and joints. It's been deformed. We know that glaciers used to be there. You'll learn about that later in the semester. So I see that this could have a mass wasting moment, including something like a landslide. So you never know when it could happen, but you should always be looking for the clues that mass wasting could occur. Because the factors, when you start to get multiple ones of those factors I mentioned in place, it is a recipe for disaster. Humans try to mitigate problems with mass wasting by implementing something called best management practices, known as BMPs. You need to know that. There are a variety of BMPs we can do to reduce the potential for mass wasting, but we'll never stop it altogether. And I need to be very blunt about that. So we can put things like nice retaining walls, rock berms. We can put in even rock bolts and rock fences. We can't stop it though. The other thing we have to do is maintain these best management practices. As soil, rocks, and stuff get behind a wall like this, if you don't maintain it, the angle of repose will get exceeded and you can still have the mass wasting event occur. So here is an example out in New Mexico of a fencing they put over really steep areas like along the main highway in Albuquerque, and they'll put rock bolts in. And when I mean rock bolts, the rock bolts can be 10 feet long. They can be huge. And they're anchoring all of that in to try to keep that slope more stable. But if rocks start to fall off and get between the fencing material and the rock face, eventually the angle of repose will be exceeded and the whole thing will pop off. So you've got to maintain your best management practices. And when you see this kind of stuff, it's there for safety and hazard mitigation. You need to realize that there's already a problem there and there could be a bigger problem while you're there. So just take safety, heed, and caution when you see this type of stuff. When you see the signs from this day forward, I'm asking you pay attention. And notice that they're not just there because government wanted to spend money on signage they didn't need to put anywhere else. They're there because there's liability and there's already likely been problems in the region. So you don't want to be that person that gets clobbered by a landslide, a rock slide, or a rock fall. You don't want to be in the place where the angle of repose is exceeded and damage occurs. Instead, you want to be on the side where you go, yeah, I knew better. I didn't do that. Sometimes it just happens even to people who are knowing and taking precautions. But oftentimes mass wasting happens and people could get out of the way or should have noticed some warning signs. And I'm wanting you to recognize those signs from this day forward. You're likely going to have questions or concerns, and that's understandable because mass wasting can be scary. And it should be. It should kind of make you go, I'm not sure about this. I'm concerned. Shouldn't let it stop you from traveling. Shouldn't let it stop you from living where you are. But I would say maybe consider those things as you purchase property. Consider those things where you're going to set your tents up, your vehicles, where you're going to choose to vacation. These are all things that may matter because this kind of stuff happens and it happens unexpectedly. And you don't want to be there when it does. In just a minute, we'll come back and kind of reset about the key things you need to take away from this lesson. But let's have a nature moment first. Kind of an interesting nature moment, huh? As you kind of wrap up with mass movements, mass wasting, and orogenic events, you need to make sure you know what a mobile belt is, the various mobile belts we have in North America, what an orogeny is, what an accreted terrain, and principle of isostasy. You need to make sure you can know the differences between flows, slides, and then other types of mass wasting events, the factors that increase mass wasting. This is a pretty simple, straightforward topic, But you do need to take some time to learn the different types of mass wasting and the factors that contribute to them. Thanks so much for your time, and I look forward to visiting with you in our next chapter's last section on hydrothermal features, which includes some of the coolest things on the planet. Actually, they're pretty hot, but cool in terms of being really neat, and that is geysers, mud pots, fumaroles, and hot springs. Bye!